All right, we're going into the last two chapters where we're talking about variables in the atmosphere for aviation weather. I know some of you have taken my earlier introduction to meteorology and know all about these variables, right? But we're going to apply them a little bit today. Uh, for example, we can talk about air motion. Air can move horizontally, it can move vertically, it can move diagonally. It can move in any direction within 3 dimensions. So, with that in mind, say you have vertical velocities, which were typically when you're flying, you feel some bumps in your aircraft, maybe. And that is vertical wind motion, either up or down. The stronger that is, the more that bump's going to be, the more turbulence or intensity there. So, if you have a growing cumulus cloud, for example, it goes up about 500 feet a minute. You get light, maybe moderate turbulence. Now, if you have a thunderstorm, that's 2,000 feet a minute. What I want you to show you is how about a strong thunderstorm? Actually, wind speeds have been clocked at over 150 miles an hour in the vertical in a severe thunderstorm. I don't think you want to be flying through there. Mountain waves, they can get really very strong as well and have extreme turbulence, and sometimes clear air turbulence. So I'm going to fly through some stuff here. I just wanted to give you a feel. This is all in the book, and we talk about divergence and convergence. What they mean is air is coming together when you have convergence. Well, say air is coming together at the surface. It can't go into the ground, so it's going to rise up. The tropopause actually acts like a surface. So when you have converging air at the tropopause, it sinks. That's why when the air is sinking into a high pressure system, where typically high pressure systems form under converging air aloft. When that happens, you wind up with air sinking, you wind up with nice weather. On the other hand, when winds are converging at the surface and diverging aloft, what's that mean is you're getting a column of air rising up faster and faster. That column of air rising that fast is probably producing lower pressure at the surface in your bad weather. So those two concepts really are showing you, if you can forecast them, you can forecast the types of weather you may be having. And you can see them here expressed. Mountains, orographic lifting. If you live in the Rockies, you're going to fly over the Rockies. You're going to have winds that are going to be going up and down over the Rockies. And most winds come from the west. So if you're on the west side of the Rockies, you wind up with the air going up. And on the east side, you wind up with it coming down. And no, it's not moving exactly all the straight down or anything. It's moving at an angle. So you can actually calculate, because it's a right triangle, we'll say, the amount of wind speed up or down there. Fronts do the same thing. The air hits the front, warm air rises over it. You wind up with air motion, vertical motion. Convection is another form of lifting. If you ever flown through a cumulus cloud, just a little one, I can remember flying into Orlando, and it's been a number of years now. And there were a whole bunch of little Q developing, and basically there were going to be thunderstorms that afternoon. This was early, mid-morning. The Q was probably no higher than 8,000 to 9,000 feet. But once we descended into that, we started bouncing around. And being a little bit of a nervous flyer, I wasn't too happy with that, but I knew what it was. And it was all the convection at the ground. Once we got below the cumulus clouds, we leveled out. Once we were above that level, we didn't have any motion either. So this was all due to lifting of warm air, convection. There can be mechanical turbulence as well. When air blows along the ground, it begins to roll, and that's called mechanical turbulence. You'll see that in streets of clouds. When you're flying along sometimes in the Midwest, especially, you'll see these cloud streaks. There'll be just all bunches of Q or stratus clouds, low level, all in rows, and you'll see several of them. That is caused by this mechanical turbulence. gravity waves are basically gravity trying to bring the atmosphere into a level motion. What happens in a stable atmosphere, sometimes these generate. When they do, they can get quite severe. The really bad ones actually can lead to severe weather at the surface. We've had some, I can remember one case where they formed during a low pressure system because it was stable air aloft and a gravity wave developed. It actually triggered winds at the surface of over 50 miles an hour and very intense snow for only a short time as the wave moved by. But that wave triggered that. Stability. Think about a balloon, a hot air balloon rising in the atmosphere. Why does it go up? It's because the air is less dense in that balloon than the surrounding air. So if you have an air parcel that's heated air pushes the molecules further apart. So you have less molecules, the air is less dense, so you wind up moving that air parcel upwards. That is an unstable air. When the air, on the other hand, gets colder, what happens? It sinks back down. It wants to go, it's always trying to find the same level of density. So you look at atmospheric stability in terms of a couple things. Dry adiabatic processes means no air, no moisture whatsoever. Dry adiabatic. So when that happens, if you lifted an air parcel, you know that air parcel, by the physics, is going to cool at 9.8 degrees Celsius per 1,000 meters. So if I look at the surrounding air, is the surrounding air warmer or colder? Most times the lapse rates in the atmosphere are between about 6 and 8 degrees Celsius per 1,000 meters. So if you got an air parcel lifting up dry adiabatically, it is most likely going to be colder than the surrounding air. So it's going to want to sink back. So there better be something pushing that air parcel up, be it a front, a mountain, whatever. Now, there's another aspect to that. What if that air parcel is now saturated? If that air parcel becomes saturated, then latent heat has been released, and that air parcel is no longer cooling at 9.8 degrees Celsius, probably cooling a little bit over 6.5 degrees Celsius. Now, say my air pressure, my air temperatures on the lapse rate and the air around that are, we'll say 8 degrees per 1,000 meter. That air parcel, 1,000 meters up, is going to actually be 1.5 degrees warmer than the surrounding air. 1.5 degrees warmer, it wants to accelerate up. So there's an actual acceleration of that air parcel due to the stability, it being unstable. So we look at that a lot. We can get sometimes during the summertime or in the spring, strong cold fronts are coming into your area. If that strong cold front is pushing that dry but moist air up, we're going to probably cool at 9.8 degrees Celsius until it reaches saturation, and then it's going to cool at 6. If that happens and the air around it is, we'll say it's cooling at about 7 or 8 degrees, that moist parcel all of a sudden has become unstable and will begin to take off. It's just going to shoot upwards as fast as it can to try to get back to where it's the same temperature as the surroundings. So that's why stability is so important in your flights, everything. It enhances vertical motion. In other words, if you can get air to rise from a big low pressure system or convergence, but then you add instability with it, it's going to rise that much faster. So I just wanted to look quickly at moisture. We know moisture can occur in the atmosphere. It's the only gas that can change state in the atmosphere. So latent heat is released when the air goes from vapor to liquid to ice. So when it is being cooled, latent heat is being released. when it goes the other way and it's freezing, it's actually adding, it's being absorbed. So in other words, when it go from ice to water, that ice had to absorb some heat. It got warmer, so yeah, it makes sense. Now, remember the air around that is also being either heated or cooled based on what is happening to that moisture. So that has implications for stability, which we just talked about, and for what kind of precipitation you're getting. So water vapor coming out of the surface of water. So, and here we can look at temperatures and saturation vapor pressures, which are just how much water vapor that air can hold. In other words, the colder the water, the air is, the less water vapor it can hold. And yes, it is different over ice because ice doesn't have molecules moving as fast. And relative humidity is just what the current vapor pressure is to the saturation vapor pressure is. So in other words, how close to saturation is that air? Dew point. To measure, if I drop the temperature and dew to a dew point temperature, dew is going to form. So, for example, right now my dew point at my house is 0 degrees. So to get dew here, I have to drop the temperature all the way down to 0 degrees Fahrenheit. Not happening today. Same thing with frost. If it's below freezing, it would be a frost temperature. The reason we put dew points on a weather map is it gives an indication of how much moisture is there, how close. You look at the dew point and you look at the temperature and you can see by approximate relative humidity. If they're the same, you're 100%. The further apart, like for example, right now I'm about 26 degrees with a 0 degree dew point, I am quite dry. So clouds are just water vapor that is condensed, but there has to be something to cause that condensation. And that is condensation nuclei. Condensation nuclei can be salt from the ocean, chemicals coming out of a plant, even dust. All those could be the things that cause air parcels to condense and form clouds. Cooling obviously causes that. You get that advection fog over the United States, fog in the valleys, lifting on a mountain. Guess what? If you're in West Virginia, you have a west wind coming down, hitting your mountains. It's going to rise up, right? If there's enough moisture in that air, it's eventually going to cool, cause a cloud. And if there's enough moisture in that cloud, maybe it'll even cause some snow or rain. That's why the air coming off the Great Lakes, coming into West Virginia, it has picked up moisture from the Great Lakes. It hits the mountains where maybe hadn't snowed for a good stretch, maybe a little bit of clouds. All of a sudden it's being lifted more. It winds up much higher up and winds up snowing on those mountaintops. And the stronger that wind is into the mountain, the more the vertical motion is, the more that snow might be. So we've talked about latent heat and stability here and that causing your different temperatures. You're going to get in cloud heights. And when you're looking at a METAR, that is the point at which you can't see through the cloud anymore. So and the amount of sky that's covered is the percentage, or broken versus scattered versus overcast. So that is how it used to be that if I was the observer, which when I started in the weather service I was, you looked outside, you tried to look at the whole envelope of the sky and figure out, okay, what percentage is covered by clouds? What are the heights of the lowest cloud first? And what percentage is it? And then the second cloud up, maybe a little higher. And then you add the two percentages together to get the actual percentage of cloud cover that is for the second cloud. That's how you will look at heights. And your observations are coded that way. Visibility, on the other hand, is a little different because what I'm doing in visibility is Say I had a building out there. Can I see that building if I know how far away it is? Can I see a light tower if I know how far away it is? And at least 50% of the visibility has to be at or below that visibility to be the actual visibility. So that is another way of looking at it. When you have clouds that are very low, say you have snow falling, when you look up, you can actually see up into the snow for a ways. At some point, you cannot. That is what the new ceiling is. So I think that is what I wanted to talk about on this part, and I really wanted to just show you something. This is a sounding this past week when it was extremely cold down in Texas and Louisiana and all. This is Lake Charles, Louisiana. However, above that cold layer, it was warm. Matter of fact, there were 2 layers of fairly warm air. If you had the ability, and you did, believe it or not, there were thunderstorms that formed. The air was rising here. So when it picked through this layer here, it was actually, this is the moist adiabat. This is the actual lapse rate over here where the air temperature was. This moist adiabat is warmer than this air. So it continued to rise. It accelerated up and actually generated some not real strong thunderstorms, but some thunderstorms. Also just wanted to take you a quick peek at GOES. There's a way to look in GOES satellite at mid-level, low-level, and high-level water vapor. And this is mid-level water vapor. If you get a quick peek at it, we'll say before you leave the airport, you can see moisture here, but notice where the moisture is coming from. I'm in West Virginia today. Look at the winds are coming out of this direction, down this way, literally, or even a little bit south into there. But however, if I'm down in Texas, there's some moisture coming up further. Pacific Ocean. So I can, if I know that, maybe I can tell how much moisture is actually coming into an area. And there is definitely more moisture coming into Oklahoma, Kansas, off the Pacific Ocean. Very dry across Florida today. So you get an idea from this where your moisture is coming from, where it might be going. It's a great way just to pick out mid-level moisture, which is about at 15,000 feet. So hope you got a little bit out of this, and let me know if you have any questions.